Let's move on to the next chapter, which is on control flow. I'd like to cover finer ways to control the flow of loops. We will learn how to break function executions, and then we will learn about exceptions and how to use exceptions for breaking out of several loops. So what is control flow? Control flow refers to the order in which individual statements, instructions, or function calls are performed inside a program. And we have already seen various ways to control the flow of code. For example, loops, branches, like if statements, and functions. Now, this lecture is about a bit more on all of these. How can we control them in finer ways? So we have already seen for loops, so that was the simple definition using the range command, and also while loops, which are executed as long as some condition is satisfied. Okay. Recall the main differences. So the for condition here, the for loop keeps on iterating until the range command here is exhausted. So until the iterator doesn't return any more values, while the while condition is executed as long as this one here is true. And this condition is only checked at the very beginning, at the head of the while loop. So this condition here might become false inside the body of the while loop, but the while loop will still execute till the end, until it comes back to the head and then checks the condition again. Okay? So that's the main difference between for loops and while loops. Now, what we want to do is we want to exit loops prematurely, or we want to be able to go back to the beginning of a loop without executing the rest of its content. Here is a function, again, which computes the sum of the digits of a positive integer, digit sum. We have seen this before. And what we want to do is we want to write a program that loads integers until 0 is loaded. And the program has to write the sum of all the digits of all the positive loaded numbers, ignoring the negative ones. Okay. Not a very exciting problem, but good enough to demonstrate what we want to do with the so-called break and continue commands. So one way of doing it is as follows. I initialize my sum at 0, and I have this helper variable called last. So last just stores the information whether the number that has just been entered by the user is the last one I want to ask for. Okay. As long as I have more numbers to ask for, I will continue with my while loop, right? So while not last is true, we will continue with the loop. We will get an integer n, and we will ask the question, well, if n is equal to 0, then this was the last number we were asking for, so we set last to be true. Otherwise, and if n is greater than 0, we want to add it. We want it to add its digit sum to our variable s. Okay. So this will really sum the digit sum values for positive numbers until the number 0 is being entered. And there's an example of this program running. If I run it with input 17, minus 17, and 0, then s after execution will have the value of 8, because that's the sum of the digits of the positive number, which was 17. That's one way of doing it. Here is another one. Instead of having this helper variable last, I could ask for the first number outside the while loop, like so. And then I would only enter the while loop when n is non-zero, because if the first number that is being entered is 0, then we stop immediately, right? There's nothing to execute. So if that number is non-zero, we will enter the while loop, and then we will check if n was positive. We will add it to digit sum, and then we would ask for the next number n here. These programs are equivalent, but both of them have some disadvantages. So what is not so good about these two solutions? Well, here in the first one, we needed this additional variable last, right? Which is kind of annoying. I mean, it's just a helper variable, but it would be nicer if we could get away without it. Whereas this one I think, is even worse because we are asking for the input for n at 2 different positions in our code. Replication of code like this is always a troublemaker, because imagine that you want to fix something in your input statement, or imagine that it's a much more complicated statement than just an input and an integer conversion. You would now have to fix this at 2 different positions in the code, right? If you notice that there's something wrong with it. So it's always a good idea to avoid code duplications as much as possible. So for this reason, this solution here is not good because of an additional variable. This solution is terrible because it basically has some replicated code scattered all over the place. Although they are formally correct, of course. They do what they are intended to do. So how can we do this better? Well, a better way of doing it is to rephrase the problem slightly as follows. We want to load numbers until we load the 0 number. We want to ignore all the negative loaded numbers. We don't want to add them up to s. And if n is positive, we want to compute the sum of its digits and add it to the sum, and then print the solution. If we rephrase it like this, it becomes very easily converted into the following program. Load an integer n, and we will do this inside a loop. If n is 0, stop the loop, nothing more to do. And if n is negative, continue with the loop. Do not execute the addition of the digit of sum to the variable s. And what we need for this, in order to have this implemented in Python, is the break keyword, which does the following. It basically continues the execution after the loop. Okay, so it will exit the loop and then just continue with your code after it. And then there is the continue statement, which will ignore everything that follows it inside the loop and go back to the header of the loop definition. So let's see how we can make use of break and continue. I initialize s to be 0, and now I'm starting an infinite loop. We have seen this before, right? So it's a loop that will go on forever unless I interrupt it. In this infinite loop, I'll ask for my integer n. If this number n happens to be 0, I want to break. So what break will do is it will just exit the while loop, and we will jump to this line here, which will print out the result. Okay, that's break. If n is negative, we do not want to add its digit sum to s, which is why I have a continue command here. So what continue will do is it will just jump back to the header of the while loop, ignoring everything that follows it. Okay. Break and continue. So let's test this out. 17. I need a digit sum function as well. (17 minus 17 or minus 18, 0). Okay, sum of the digits of positive integers is 8. So this works fine. Now, this solution is much better than the other two. Why? First of all, it doesn't use any additional variables like the last variable that we had. And also, we are asking for the input of the user at exactly 1 position in the code and not at 2. So with break and continue, we can organize our codes in a much cleaner way than without. Of course, we need to be careful because we have an infinite loop here. So whenever you write an infinite loop, make sure that there's definitely a condition that can be satisfied at some point with a break. Right? The only way to exit an infinite loop without producing any errors is to use the break command. So when you have an infinite loop, make sure that the condition that is associated with break can actually be satisfied at some point. Otherwise, we will keep on looping forever here. Now, break and continue exist in most programming languages, also in MATLAB, for example, or in C. And usually they have exactly the same meaning there. And infinite loops have nothing to do with break or continue. They exist independently. And it's important to remember that an algorithm is a sequence of finite steps, so infinite loops need to be broken at some point in order to have our algorithm produce a result in a finite number of steps. We can have nested while loops, of course. We could have a while loop which loops until or as long as condition 1 is satisfied, and inside this while loop we could have another while loop, and then inside the second while loop we could have an if statement with a break condition there. What happens in this case? Well, it turns out that Python will only break the innermost loop. So when break is encountered here, inside this while loop, it will actually break this while loop, but it will still be within the outer while loop, which will continue looping. Yeah. So important to remember, both break and continue only affect the innermost loops. And it is not possible to use break outside any loops. So for example, if you define a function like this, that would result in a syntax error. It's not allowed to use breaks or continue as well outside the loop. Not even in this way, where I have a for loop, and inside this for loop I'm calling a function which has itself a break. That's also not allowed, right? Now this helps us to simplify some of the programs we have seen before. So here was an example from 2 weeks ago where we input a list of integers until -17 is loaded, and then we want to print all of these numbers in a sorted fashion. So that's an example of loading a list one after the other, which we of course do by starting with an empty list. As long as we are not done, using this Boolean variable not done, we would ask for integers. If an integer is -17, we set not done to be false, which would then stop this while loop. Right? So we have seen this before. Now using break and continue, or break only in this case, this becomes much easier. We start with an infinite loop. We ask for the first element in our list. If an element happens to be -17, we will break the while loop. Now this break will stop the execution of the while loop and therefore not execute the append here. Right? So the last element that is being asked for, which was -17, will not be appended to the list because it follows the break statement. So when I call this program here with input 17, 19, 13, -17, the list that is being produced does not contain -17. What would I need to do in order to have -17 in the list? Well, all I need to do is I would need to swap the append operation with the check whether to break or not. If I want to have 17 included, all I need to do is to swap these two. Now for the same sequence of inputs, 17, 19, 13, -17, I would have -17 in my list. Okay, what else can be done? Well, in fact, we can use the else keyword in combination with loops. So when is this else block executed? It is executed if and only if the loop was not terminated by a break statement, but by the condition that defines the while loop. So let's look at this example here. I have some number n, which is 17. I have a while loop that goes on as long as n is positive. And I would ask for some integers n, and then when n is 0, I will break the loop. And then I have this strange else command here. So what does this do? This part here, this else part, will only be executed when the while loop has stopped, but based on this condition here. Namely, when the initial n is 0 or negative. Right? This is the only point when this else command is executed. It will never be executed when I stop the loop with the break keyword. So let's test this. Okay, I can continue entering some positive numbers. I'm still stuck in the while loop because it goes on as long as n is positive. Now, if I enter a negative number like -7, this condition here will no longer be satisfied the next time we come back to the header of the loop. So the else part is being executed. Okay, the loop wasn't terminated with a negative number. However, when I enter 0, now the loop will break because of this break statement, and therefore the else block will not be executed. Okay, not producing any output here. And again, very careful with indentation. Of course, this is different from this code here. So if the else is part of the if command, we will get a different behavior of our code. So really, this else block here needs to be indented on the same level as the while block in order for these two to belong together. How do we break the execution of a function? We have already seen the return keyword, right, which immediately terminates the function's execution. And this return can be very useful if we want to do various tasks without introducing some extra variables. So what do we have here? We have here a simple piece of code that takes an integer input. It checks whether n is less than 2, in which case we are sure this is not a prime number. Else, it could be a prime number, so let's just assign is prime the value of true. If it could be a prime number, we need to check whether n is divisible by d, right? So we check all the possible divisors here. If we find a number d that divides n, we are sure that the number is not a prime number, so we will set is prime to false, and we will break. So what does this break here affect? Well, this break affects the for loop. As soon as I found a number d that divides n, I can just exit. I don't need to look at the others anymore. And when we are done, we can print whether the number is a prime number or not. Here's another way of doing exactly the same thing, slightly shorter, but what I want to come to is this implementation here, which is much more elegant. So this does exactly the same thing, but now using a function. If n is negative, we return false. Now, because return stops the execution of the function, we do not need an else block here, right? There's no point having else here. Return will actually execute, exit the function from the beginning. If this return has not been executed, we continue checking all the possible divisors d. If we find one such divisor, we return false. Again, the function will be exited. We will leave this function and therefore terminate the for loop. If we come to the end of the for loop without returning anything, we are sure that we have a prime number, so we can return true. That's the most elegant of the solutions that we have seen so far. It doesn't use any helper variables like is prime true or false. It doesn't have any repetitions of statements. It's basically just a function with a few return commands here. So in the future, whenever writing a function, make sure that you first think a little bit about organizing your code, because doing things in the more elegant way will save you a lot of work later on, potentially. It is always a bad sign if you end up having more than, let's say, 2 nested if commands or nested while loops or nested for loops. Right? We typically want to avoid nested statements as much as possible. In this code here, we have only a for loop with 1 nested if command. Right? Now, just to show you, the same can be done with a list comprehension, of course, much easier. So we get an input argument n. This can only be a prime number if n is positive. So we need to check whether n is, and in fact, greater than 1. So we check whether n is greater than 1. And this goes through all the possible divisors d, and it checks whether n divided by d leaves a positive remainder. If this is the case for all numbers tested, then this will evaluate to true. And if also this evaluates to true, we are sure we have a prime number. Okay. Exceptions. That's a very important topic because it will prove very useful for making our codes more robust and less sensitive to the user providing wrong inputs. Okay. So basically what exceptions are for is the following. If we have some commands to be executed, so let's say some loops, function calls, or things that we are calling within our code, we want to be able to handle unexpected cases in a very elegant manner. So let's look at an example because I think it makes it easy to understand. I have a simple program here which imports the square root function, so I want to compute the square root. I'm asking for two floating point numbers as inputs, and then I just want to output the square root of the first number divided by the second is equal to the result, and I'm using the format function here. Okay, so let's say this is one of the lab tests, and we are just playing with some parameters. So let's test our code. What is the square root of 5 over 2? Okay, that's the square root of 2.5 is some number there, right? Okay, you can compute square roots quite easily. Now, are there any potential problems that can arise with this code? Is there something that can go wrong in the user inputs? Exactly, right? So what happens when b is 0? Well, let's try it out. A is 5, b is 0. Oh, there we go. So 0 division error. So our code that we have written just stops execution and prints out some cryptic error messages that a user might not really be able to interpret. Right? We certainly do not want this behavior. Is there another potential problem? Yes, it turns out that when A is negative, say, and B is positive, we end up with the square root of a negative number. And the square root function that I have imported from the math library can actually not deal with square roots of negative numbers. Okay? Because it does not work with complex numbers out of the box. So in this case, we again get an error, in this case a value error stating math domain error. Math domain error means you have tried to call a function with an input argument that is not in the domain of the definition of that function. We have called the square root function with a negative argument, so negative numbers are not in the domain of that function, therefore we get this particular error. Now interestingly, the error messages that we get, they contain a lot of information about what was going wrong. So in the first case, we got a 0 division error, which is a clear indication of the fact that we have decided to divide by 0. Now what you see here is an unhandled exception that has been raised. And the way to catch these errors and treat them manually is to take the code that we are working with and wrap them inside a try except block, like so. See? It's exactly the same code as before. These are the 3 lines, the inputs and the outputs. But I've now wrapped this inside the try keyword. And then I have some other part which starts with except, and then the name of the exception, colon, and then some print statement in this case. So let's try the same code and see what happens in this case. Okay, let's try A being 5 and B being 2. We get exactly the same answer as before, no problem. Let's try 5 and 0. That should give division by 0. And indeed, what happens now is that we have entered this exception block here. So we have kind of treated this exception that was raised by this division here in our own exception block. And likewise with negative numbers, so minus 5 divided by 1, again we get your A and or B are wrong output on the console. You see the program did not crash no error messages were produced on the console, and if there was some other stuff going on here, some other Python commands, they would be executed as normal. Okay, the program would not stop. So that's the syntax, try and accept. It is possible to omit this exception variable here, but it is not recommended. So the general form should be at least of this format, try and accept exception. That's the way to do it. So that's the minimum requirement. Use this exception variable here. Now, what is this actually for? Why do I need to write accept exception? The reason for this is that there are different types of exceptions that can occur. We have already seen different types when we called our program. So the first time we called our code, we got a zero division error. It's one type of exception. And the other time we got a value error when we tried to compute the square root of -1. So these two are different types of exceptions, and we can distinguish between them. And that's the way to do it. So I have now replaced what was exception with the more specific zero division error. Okay. So let's try this. I'm doing A5 and B0. We know that the division that is here, A divided by B, produces an exception of type zero division error. And because this exception fits with what we have written here, this part of the exception block is being executed. Okay, let's try the other one. 5 and -1. That was the square root of a negative number. Well, that's an unhandled exception, right? We have not really dealt with this error, so we are returned with a value error. So how can we make sure that we capture both cases? Well, all we have to do is we have to add another exception here for value errors. So that was a square root of a negative number. See? 5 -1. There we go. So we have now treated these two possible exceptions that have been produced before and caused the problem to start and crash. We have now dealt with them in a very elegant manner. Okay, so that's also explained here. Of course, it's possible, just as a side remark, to do complex arithmetic in Python. If you want to do this, you need to import the C math package. So C stands for complex. It contains essentially the same functions as the math package, but with complex functionality. Right? So when you then compute a square root of a negative number, you will get both the imaginary part and the real part in the outputs like so. In fact, let me just show you how this works. So I get the C math package. And I'm just computing the square root of -5. And now we can get the result .imag, which will return the imaginary part of the result, which happens to be 2.23 and so on. Okay, so that's the imaginary part. And the real part, of course, is 0, right? Because it's a purely imaginary number here. So. Okay. Now these try except blocks can have another block, which is the else part. So the else part is executed if no exception has happened in the try block. So here's an example. Again, we have our critical computation, which might produce errors inside the try block. We take care about zero division errors in this part. We take care about square roots of negative numbers in this part. If none of these parts is being executed because no exceptions occurred, the else block will be executed here. Right? So that will do the same as before. It will print out the result when no exception occurred. And if one of these exceptions occurred, then we enter the corresponding block, and the else part is not executed. So question is, what is the difference between doing it this way with an else block or doing it like this without an else block? Is there any difference? There is a difference in the sense that we are not 100% sure that all the exceptions that we are currently handling are complete, right? There might be some other errors that we haven't thought about at the moment. So if this was the case, there would be a difference in the two. All right? So that's important to remember. The else block is only executed when none of the exceptions occurred, while we are not completely sure whether actually zero division error and value error are all the exceptions that can possibly occur. There might be others. So, well, that's basically the same thing without exceptions. So we could, of course, manually check whether b is 0, and if it is, then we would just refuse to divide by 0. And likewise, we could also check whether what we have just computed, the quotient of a and b, is a negative number, in which case we would not try to compute the square root of a negative number. We could always do this, but one thing that you see immediately here is that we are dealing now with two nested if statements, whereas the code before didn't have any if statements. So immediately, without having exceptions at our disposal, our code becomes much more difficult to read, and as a consequence to debug if there's a problem in it. So this code is not very nice, and in particular, if we had a more complicated task where we need to check more things, we would end up with maybe 5 or 10 nested if statements and would make a completely horrible code to read. So while it is sometimes possible to avoid exceptions, even though it doesn't look very nice, there are cases where we actually need them critically. And one of the tasks is something that you have seen before, namely, how do we make sure that the user enters a floating point number? Okay, let's say we ask the user to enter a floating point number. How can we manually make sure that what they have provided is indeed such a number? What we have done so far is we have used input in combination with the float function, which takes a string as an input and converts it to a floating point number, let's say x. And you might have already seen that this can fail. So let's say I have something like this, and I type in a number like this. We have an error here, right? We get in particular a value error because it is not possible to convert the string that I've just entered into a meaningful floating point number. That's just an exception that has been raised. So what we can do now is we can use exceptions to make sure that users actually provide us with values that can be converted to floating point numbers. We can treat these cases now in a very elegant manner. And by the way, checking whether a number is indeed a floating point number is a non-trivial task, right? So here is a floating point number, minus 17.19. Well, the first thing you would need to do if you wanted to check manually whether the string is a floating point number is you would have to check whether at the beginning there's a plus or minus, right? Because that's definitely allowed by entering floating point numbers. Then that you have digits and a decimal place. So it might be actually possible manually to check whether this string here represents a floating point number, but as soon as the user inputs something like this, which is in fact a valid floating point number. That's minus 1.719 times 10 to the power 1, right? It's a valid number. You see that would be immediately much harder to check. In fact, this conversion function here also works with spaces. You see, when I input a number, a string, and I put some spaces in front of it, let's say like this, my program executes without any errors, meaning that this conversion to floating point has actually succeeded. So just to make a long story short, floating point numbers internally can be of a very complicated format entered by the user, and still they are valid, and it would be completely impractical for us to check all possible cases. So let's just let the float function take care of this using exceptions. And here's the way to do it. We'll start with an infinite while loop, because we don't know in advance how many tries the user needs for entering a number. We will put the conversion of the string to a floating point number into a try block. Right? So we'll now handle possible exceptions that are being raised. And if an exception occurred through this conversion, which was a value error exception, remember from before, that's actually outputted here, right? When we encounter such a value error exception, we just print out that the number was not a valid floating point number. And what happens next? Well, we are in an infinite while loop, right? So we will just continue asking for the next number. Only when the number conversion has succeeded, meaning that the else block is being executed, we will break the infinite while loop. So let's test this. Input a real number, doesn't work. Input nothing, doesn't work. Succeeded. Okay, so a very robust way of dealing with user inputs. A small comment. Typically in practice, it's much easier to check whether an input is valid compared to checking that an input is invalid. Right? So positive checks are easier to perform usually than negative checks. So it's best to use exceptions. Just assume that the user is inputting the correct value and then deal with cases where things like this break, where you get an exception. There is yet another part to try, except, and else constructs, which is the finally block. Okay, so this here would be a perfectly valid definition of a try except block. So you have two functions that you're calling with names do something 1 and 2. If some exception is being raised, we deal with it. So we call another function called handle exception. We have already seen that when no exception has been raised, no error is going to be executed. And then there's another one which is called finally. So finally does the following. It basically is always executed no matter what happened above with the exceptions. So let's assume that no error occurs when calling these two functions. Which of these functions are actually executed? Well, do something 1 and do something 2 are executed because there was no error. Because there was no error, we will also execute this block here and then wrap it all up, right, in the finally part of the construct. Now let's assume that do something 1 produced an exception. What is the flow of the program in this case? Well, do something 1 is executed, but then an exception occurred and therefore this second function was no longer called. We will therefore jump to the except block. We will handle the exception and then we will go to finally, which wraps it all up. Okay. What happens if some other exception, so an exception that is not handled by our program, occurs when we call do something 1? Okay, we call this function. It produces some other exception. The interpreter will look, are you actually handling this exception? No, you're only handling some exception. Therefore, this part is not being executed. This part is not being executed, but this one will be executed. Okay, and then finally, this other exception will still be raised and cause your program to finish with an error message. Okay. So it's important to remember that the finally block is always executed before the try block is completed. And finally, will even be executed when you're leaving the try block with a break command. So in this particular example here, I have a try block where I'm checking whether a certain number n is a complete square of I. If I find such a number, I will break, and even when this break occurs, finally will be executed. It's important to remember that finally itself does not catch any exceptions. So if you put some code into the finally block, which itself produces an error message, then your overall program will crash. So it is not possible to, or it should be avoided to put any critical code in the final block which could potentially cause any exceptions itself. Now a few general rules. There are different types of exceptions, and it is always good to catch the exceptions in the most specific way possible. There is indeed a list, which is linked in the lecture notes, of all the exceptions that are available in Python. Okay, it's part of the Python documentation, so-called built-in exceptions. And you will see that it's a very long list of all possible things that can potentially go wrong in your code. So let's look, for example, for the value error that we have used already. Value error. Here it is. Now each of these exceptions has a precise description of when it is the appropriate error message. So a value error occurs when an operation or function receives an argument that has the right type but an inappropriate value. Okay, so that was the case when we called the square root of a negative number. It was a number. We used the floating point number as an input, right? So it had the correct type, but the value was inappropriate because it was negative. Therefore, Python decided that this should be raised with a value error. Let's look at zero division error. The zero division error is raised when the second argument of a division or modulo operation is 0. Well, it's quite as we would expect it to be, right? So it's good to look at this list whenever you encounter errors and choose the most specific one from this list in order to give meaningful error messages to the user of your program. Okay. So exceptions also work across functions that you're calling from within a try and except block. So here is an example that I'd like you to have a look at home, possibly. It's a simple function that takes 3 inputs, n, f, and t, and all it does is it has 2 nested for loops for I and j, and in these for loops it computes the quotient of I and j, right? So that's all it does. Now the range of j is between f and t, where f stands for floor and t stands for top. That's how you can think of it. And clearly we can run into problems when j traverses a value of 0, right? Because then we get a zero division error. Now, even though this error, this potential zero division error, occurs inside a function called f, you can still catch it from outside that function if you wrap the function call into a try block like here. Right? So you see, I'm calling this function f within a try except block. Now the interpreter, when it executes your program, will execute f, and as soon as it encounters a zero division error, it will stop the execution of your function, go back to the try block it came from, and then see, well, the zero division error is actually handled, therefore I'm going to print out an error message here. Right? So the errors that are being produced do not necessarily come out directly of commands that you're writing inside the try block. They can also be produced by functions that are called within the try block. Right? So that simple example here if you run this with different values of n, 2, 5, and 11, you will see different behavior, illustrating that you can indeed catch exceptions that are raised within functions, also outside that function. Okay, so these exceptions are all predefined. How do we actually produce our own exception? That's what we're going to learn now. Here's an example of a function that should actually raise an exception for particular types of inputs. This function is called arithmetic mean. It takes an integer value n as input. It will then ask for n integer values to be inputted by the user. That's done in this for loop here. And as we go along, we keep on updating a running sum underscore. And after the last number has been entered by the user, we want to return arithmetic mean of the numbers that have been provided. So here's an example. If I call this function with parameter 3, it will ask me for 3 numbers to be inputted. Let's say they are 17, 19, 23. Then it should return, afterwards, it should return the arithmetic mean of these 3 numbers. Now, of course, there's a problem when I call this function with the input parameter 0. Right? What will happen? Well, if n is equal to 0, then certainly I get a problem here in this final return statement because I'm computing some number divided by 0. In fact, 0 divided by 0. Now, that's not a big deal because, in fact, Python will produce an exception in this case, and the exception will be 0 division error, as we expect. Now, in general, this is, however, not a good way, because imagine this is now a much more complicated function that does some more involved computation. And at some point in this computation, we encounter a 0 division error. Someone using your function as a black box does not even know that you're dividing by 0, so they will be very surprised to see a 0 division error. Right? And this is why we should here define our own exceptions with a much more descriptive error message. So another problem that can arise is when I call this function with a negative input. So when I call arithmetic mean with input minus 17, it essentially means that I want to input minus 17 numbers. This doesn't make any sense. The code will actually run without errors, and as an output, it will print minus 0 as the arithmetic mean. Again, that's an input that we certainly do not want to be handled in that way. So how do we deal with this? Well, we might want to raise our own error message. And here is an example code that shows you how to do this. The only thing that I've changed from the previous code that you have seen is these 2 lines here. We get our input n from the function header. And the first thing that we do is we validate the input. So if n is less or equal to 0, there is no point asking for n numbers. Therefore, we will raise n value error ourselves. Okay, and that's the syntax for that. It's just the raise keyword. And then it is the class of the error. In this case, it would be a value error. And then optionally, you can provide in parentheses a string that gives a more precise description of the error being produced. In this case, we might say arithmetic mean of 0 or less numbers is undefined. Right? That would be descriptive. Now, why have I chosen to use the class value error for that? Well, this is because there is this list of built-in exceptions that I already showed you last week. And essentially, I've gone through this list and I selected the class of error that corresponds to what I'm going to deal with here. So let's go again to the definition of value error. Here it is. And the description is given here. So this is raised when an operation or function receives an argument that has the right type, but an inappropriate value. And that's exactly what we have here, right? We have an integer n. So the type is correct, for example, when n is 0 or minus 17, but the value is inappropriate. I cannot really deal with negative or with negative numbers or 0. Okay, that's the syntax. Raise, class of the error, and then in parentheses an optional description. Now let's see how this works. Let's say I've defined my function with the error being raised in appropriate cases, and I'm now going to call this function with an invalid input of -3. Then the code will stop because an exception has been raised, clearly. But now it's not showing something like zero division error or a strange output. It actually shows us that a value error occurred, and the description that we have provided is also printed to the console. So someone using our function can now go and investigate and understand why a particular error has been raised. And of course, we can now catch these errors in our own except statements. So if I can now wrap this into a try except block, the error that I'm going to catch now is a value error. And now it should be caught, right? When I run this function, I should just see invalid argument printed out, and this is indeed the case. So our function has now provided the correct information needed for calling it within a try except block, like so. Okay, that's also shown here. That's exactly how we can use the function now. Now in the future, you should always aim, whenever you write your own functions, to make sure that in exceptional cases an appropriate exception will be raised by your function. Okay? It should not be able to crash your code just because I'm providing wrong input arguments to a function. By the way, it's also possible to get this descriptive string that we have defined inside our function explicitly. So this syntax here is very useful often. You have again try except value error, and in addition you type something like this s variable name. So in this case the variable name is e. Now e will be the string which describes the error, right? So you actually have access to this description explicitly in your code. So e will take the value arithmetic mean of 0 or less numbers is undefined. So you can actually use this inside your program to use the exception that is being produced inside a function to be printed out to the console in a nicely formatted way, for example. You could say, when the exception occurs, you could say, sorry, something went wrong in your input. And you could just use the exception of the function itself to produce the error message. Okay? And that's how it's done. Except type of the error as e, and e is then the string with the description. Now sometimes we want to handle exceptions like silently, which means that whenever we don't get the answer of our function that we wanted, so for example, if the arithmetic mean is not defined, then we will get an error here. But then in the except block, we might then say, okay, if there's an invalid number being computed, then we will just set am to have the value 0, so that further down in my code I can continue using this number, right? So with try and except, you can make sure that certain variables are always defined, irrespective of whether or not the function that has been used to define them raised an error. Right? So when we end up at this position here where the print result is, then it doesn't matter what n was, we will always have a value for am available in our code. Any questions? Okay. Now sometimes we want to ignore exceptions. We know that our function has some problems, but we are not really too bothered about it, so we just want to continue in our code. And this is called silent exception handling. And we might first think to do it, for example, this way. So let's say we try to divide 0 by 0. We know this raises an exception, zero division error, but let's say we want to just ignore it. So we would have something like this, right? An empty exception block. Now let's see what happens when I actually do this in Python. Okay, and we get this error that I've seen in some of your test submissions previously. It is actually not allowed in Python to have empty blocks. So as soon as you have except as a keyword here, and you end it with a colon, Python expects you to have a block. And it's not possible to have an empty block like this. Okay? This causes these so-called indentation errors because there's something indented which is not actually there, therefore Python will complain. So what do we do here? Well, the trick is to use a command called pass. Okay. It's basically a placeholder for doing nothing. Okay, so whenever you have an empty block, you might just put pass there and it will run without any errors. Okay, Python is happy now. So pass is my favorite Python command because it does nothing, right? So it's very lazy, and you can use it in several contexts. For example, you might have an if-else block like so. N is an integer. Whenever n is greater than 17, you don't want to do anything, so you just put pass here. It's not possible to leave this empty. There needs to be a non-empty block. And else, so when n is less or equal to 17, you want to print out some string. Okay, now you know how to do it. Okay. Of course, this doesn't make a lot of sense because there is a much more elegant way of doing the same thing. Instead of having an empty if block, you might just reverse this condition here and get rid of the else block instead. Right? So it would be much better in this particular case here to use this syntax. If n is less or equal to 17, then print, otherwise don't print anything. A typical use case of pass is when you want to create placeholders in your code. So let's say you have written an if-else block, and you currently do not know how to do the if part. You want to keep it empty. So why not just put a pass here and then a comment that tells you, well, I need to revisit this. When I come back, I will write the code for that. Another application of pass is to write your own error classes. And this is how to do it. We use for that a keyword called class, which defines a class of error in this case. Each error needs to have a name. So before we had value error, zero division error, but you can come up with your own errors. So let's call it some new error. And this here means that we will use the general exception class that exists already in Python to derive a new class of error messages. So we will start not from scratch, we will just actually use a generic exception and produce our own, which is called some new error. This error class itself doesn't do anything, so it's just empty, but it's not allowed to have empty blocks, therefore we need to put at least pass inside this class definition. Okay, how can we use this? Well, after we have defined our new error, called some new error, we can raise it, like any other error messages. Okay, so some new error is now like all the others in the list that I've shown you before. You can raise it and accept it as you like, and it will have your own name attached to it. A convention in Python is that all the classes that correspond to errors end with the name capital error. Okay, you can see this in this list here. All of them have names that end in error, and that's just a convention. It kind of makes sense, right? If we are dealing with error classes, this should be reflected in the name of that class. So whenever you define your own exceptions, make sure that you adhere to this convention. The last word should be capital error. We can actually use our own exceptions to break out of several loops. I told you before that we can use break to stop the execution of the innermost loop, which could be a for loop or a while loop, right? That's what break is for. We discussed this last week. But exceptions can actually be used to break multiple loops at once. So here's an example. I have defined my own exception, which is called break exception. Okay, so that's just the name of it. And what I have here are 3 nested for loops for I, j, and k. Each of them running from 0 to n, where n is some number that has been provided by the user. And all that these loops do is to compute at every iteration the sum of the 3 indices, I plus j plus k. Okay. I'm going to output this sum, so that's what this formatted print statement here does. And whenever the sum is equal to m, which is another input provided by the user here. So whenever s is equal to m, we want to stop the loop. Now, I want to actually stop all of these loops at once. How can I do this? Well, the trick is to raise an exception, right? Because when I raise an exception within a try block, I will stop the execution of the try block and just jump to this part here. So this means as soon as this exception here is raised, the j and the k loop, which are the 2 loops inside my try block, will be stopped. And I'm just left with the I loop, which is outside the try except block. So that's kind of an interesting way to skip multiple levels in this nested hierarchy of loops. So here is an example. If I set n to 3 and m to 3, I will compute all of these consecutive sums of the indices I, j, and k. And as soon as this sum is equal to 3, which is equal to m, I will stop. So this print command here will be executed and the exception will be raised. And you see we are no longer increasing the value for j and k. We're just stopping here. But the outer loop for I is still active. So after I have stopped the j and the k loop here, I can increase I from 0 to 1, and I continue, right? J and k will go from 0 to n respectively until their sum is equal to 3, and I will stop. I will go back to the outer I loop, which now takes the value of 2, and again the last stop will occur when the sum of I, j, and k is again 3. Okay, I've chosen this name break exception because it's a good name in this particular task. It is almost always possible to rewrite your code, which is also called refactoring, in a way that it doesn't use any exceptions, if you use it for these particular cases of skipping loops. So another way of doing the same thing that I've done here is to take the 2 inner loops for j and k, which are here and here, and put them inside a function. Because we know we can break out of functions using a return command, right? So as soon as return is called inside a function, that function will be stopped in execution, and I will go back to the main program. So what I have here is the outer loop for I, which just runs as before from, let's say, 0 to 2. And then I have the 2 innermost loops for j and k inside my function. And here's the same break condition. When s is equal to m, I will just print stop and return. Now the return has a similar role here as the exception in the other code. It will stop the execution of this inner loop and go back to the main program for I. So this has exactly the same output and behavior as the previous program, but it doesn't use any raise exception commands.